Signals are everywhere. They're all around us, they're inside us, they're underwater, they're in deep space, they're online, they're offline, they're really everywhere. In this new video series on signal processing, we need to start with signals. This video is just about signals, what they are, and the difference between analog and digital signals. So, what are signals? A signal is any informative quantity that varies. We have to be able to measure it, and the measurements have to mean something. To be a signal, the measurement has to be taken repeatedly over some dimension. Usually we use time, but it's also common to use space or frequency. That definition is a bit vague, so here are a few examples. Signals could be physical, like a time-varying temperature, position, voltage, chemical concentration. An image is a physical signal with spatially varying color. And if an image is also time-varying, then it's a video signal. Frequency-varying signals that are also time-varying include the outputs of wireless transmitters and musical instruments. Some non-physical signals include product prices and words, though word signals become physical once they're spoken or written down. If the measurement doesn't mean anything useful, then we have noise. Noise can also be mixed in with a useful signal, say because of imperfections in our measuring equipment. We have a couple of important ways to classify or categorize signals, which informs how we model them mathematically. First is how a signal varies over time. If a signal can vary and be measured at any moment, then we call this a continuous time signal. If a signal is only measured at specific instants, then we call this a discrete time signal. Real-world signals tend to be continuous time, but computers work best with discrete time signals, so we often have to convert between these two. A second way to classify signals is how their measurements vary. If a measurement is limited to a specific set of values, like the number of apples in a basket, then the measurement is discrete. Otherwise, the measurement is continuous, like the exact temperature in a room. We usually combine these two classifications. Continuous time signals are often continuous in value, and we call these analog signals. Discrete time signals are often discrete in value, and we call these digital signals. The mathematical tools for modeling analog signals are different from the tools for digital signals. I will be covering both of these in future videos. But that's all for now. Thanks for watching. If you liked it, let me know. Can you think of any other examples of signals? This video is part of a series on signal processing. There's also a lecture notes PDF linked in the description. If you'd like to stay up to date, then consider subscribing. See you next time.